Okay, today we're going to talk about equilibrium, and so let's just jump right in. So, we're not just talking about equilibrium, we're talking about dynamic equilibrium, and the question is that any different than regular equilibrium? And the answer is absolutely yes. But let's define what equilibrium is first. And it is the state where the concentration of all the reactants and products remain constant over time. Now, you may see that I just did this weird double bracket here, and that means concentration in molarity. And all of our problems we're going to be working with in this unit are going to be in molarity. So whenever you have a reaction and you have the reactants and products concentrations no longer change, you are at equilibrium. And what's important to understand here is that it occurs when the forward rate of the reaction equals the reverse rate of the reaction. Now, it's really important, and I used to use the example of a teeter-totter, and that threw people often. It does not mean that the concentration of the products and the reactants are equal. So typically what happens in an equilibrium is you start off with reactants, and if all you have is reactants, the only place you can go is towards your products. So the forward rate will be stronger, or will be the only thing going at the beginning. But as you start getting more and more product forming, those product molecules look at each other and go, hey, remember how great it was when we were back over on the reactant side? And they reform reactants. Eventually, the forward rate and the reverse rate, so at the beginning you have just the forward rate going, and then you have a few of the reverse reactions going, and then eventually they get to, I did not do the fingers very well here at all, eventually the forward and the reverse rate are equal to each other, and that's when you have equilibrium. Better stated, you have dynamic equilibrium. And the idea is this. Take a look at our diagram here. Let's pretend you have a parking lot over on this side and you have a parking lot over on this side. And you have a certain number of cars here and a certain number of cars here that are allowed to be. The forward rate and the reverse rate are the same, and that keeps the number of cars in each parking lot the same, even though there's cars traveling on either side. Let me use a better example here. So the question that we're going to have throughout this entire unit is, how do we know how much product and how much reactant we have at equilibrium? And that's always going to be determined by something called the equilibrium constant, or K. So I'm going to recreate this delightful diagram here as a bridge. So here's our bridge, and then down below we have like rocks. These are rocks, and then you have water, and then you have like sharks. That looks not at all like a shark with big teeth. And they have laser guns, just in case if you fall to your death. That doesn't kill you, the things in the water do. Man, that's a terrible drawing. So imagine, if you would, this is a huge cliff area here down below. And on this side you have, we're going to have a parking lot on this side of the bridge, and we're going to have a parking lot on this side of the bridge. And standing here guard is an evil alien overlord. He has a hat that says K, and he's really mean, and he determines how many we're going to use a car example. And so on one side we have, let's say, 9 cars to start with. So we have 9 vehicles on this side right here. Well, I'm going to draw them like this. You can see that there's 9 cars. They have no wheels. Oh, they do have wheels. Decided for wheels. So this guy says that the K is going to be equal to 2. And what that means is that this side, the product side, so to speak, has to have double the number of cars as the reactant side does. Now, here's the thing. There are these walls on these sides here, so you can't get out or anything. The K says, hey, if you don't get to where there's 2 times as many cars on this side of the bridge as there are on this side, immediately all the puppies in the world die. And for those of you who are like, well, I don't care about puppies, and then also everyone in the world dies. So very, very stern, evil overlord, right? So what should you do if you have 9 cars on here? Wouldn't you immediately start sending cars over to this direction right here, right? So if you were to do the math, wouldn't it make sense that if you were to get to the place where you had 6 cars on this side and 3 cars on this side, wouldn't you be fulfilling the the overlord's demand that there be twice as many cars on this side as this side, right? So let's say that happens, and you're like, "Whew, we've met the evil overlord's demands," and then all of a sudden, there's a car on this side driven by. It just happens to. I need to know the story. It happens to be driven by a teenager, and the teenagers are like, "You're not my real overlord. I do what I want," and starts whipping across in this direction. Now, everyone understands that if this ratio changes from 2 to 1, you guys are toast. So if this car makes it back over here, then the ratio is going to be off. So what should you do? Well, someone on this side is like, well, I'm going to then go across this direction so that the ratio between the products, and we'll just call this the product parking lot, and this is the reactant parking lot. So as this one car comes across to destroy the ratio, if this other car starts coming across at the same rate, then wouldn't that cause the ratio to stay the same? And then, of course, other cars on this side say, well, wait a second. If he went across, I'm also going to go across. And then these guys are like, oh, poop. We don't want all the puppies in the world to die, and also us. They may maintain the same rate. So if you look back up at our diagram, what ends up happening is we can have completely different number of cars in this parking lot over here. So we can have a huge number of cars in this parking lot on this side of the road, and we can have very few number of cars on the parking lot on this side. But as long as the rate of the cars going in one direction and the other direction remain the same, you're going to be at equilibrium. The numbers here and here will remain the same. Probably a better example to use, and I'm always searching for examples to relate to you guys, is we're going to go to, and we're not going to use just a dance example. We're going to use the example of a Victorian ball. Because again, I know my constituency, and I figure that this would relate to you really well. Now, if you've ever been to a ball, and of course you probably have, you're going to have the ladies and you're going to have the gents. And again, this is not a high school dance. Again, it's a Victorian ball, but I'm not going to write it again. So if you've ever been, as again, you have been probably, what ends up happening is you have the gentlemen, they step towards the middle, and then the females, they step towards the middle, and they pair off, and they dance, right? So if we're taking a look at, and we'll make color differences here just to make it really obvious. So we're going to go with blue. So at the beginning, you're going to have all of this is the spot for the gents, and here that we'll make another spot here for the ladies. Okay, you have a certain amount of gents and a certain amount of ladies at the ball. Now, as they step onto the floor, what's going to happen is you're going to lose some of the individual ladies, and you're going to lose some of the individual gents. And then simultaneously, you're going to start forming in the middle, you're going to start forming couples. Now, after a period of time, what ends up happening is you have the same number of the number of gents and the number of ladies, they stay the same. So you matched up everyone, right? And the couple number stays the same as well. Won't get this analogy, right? So essentially what you have is you have a group of gents, and you have a group of ladies, and they form couples. Now, here's what ends up happening here. As the couples break apart, there are others that step in. So constantly the number of, and if you've ever seen how this works, if you have a line of the gents and a line of the ladies, they dance and whatever, and then they separate back apart and they move down and they dance with the next person. They step apart and they move down with the next person. So essentially what ends up happening is that every time a gent and a lady forms a couple, right, then another couple breaks apart and forms the gent and the ladies. Now, You are never going to have the same number necessarily of couples and ladies. Now you could, but if you have extra gents or extra ladies to begin with, you're going to end up with leftovers of one of the two. So if there's the room, right? This is your room. You're going to have the people in the middle. They're all dancing, right? These are people looking from up above, and then you're going to have like a group of the guys, and they're going to be all over here. And then you're going to have a group of girls, and they're all over here, or ladies, and they're all over here. And then as these guys leave, break apart, new people jump in because there's only a certain number of people that can be forming the line in the middle at a time. So this arrow right here indicates that we are at equilibrium. And it also, if you take a look at it, it kind of looks like forward and reverse are equal to each other. So if we were to do this normally, we would say we draw one arrow to write a forward reaction, we draw another arrow to draw a reverse reaction. And often what they do is, to make it really cool, is they draw a half arrow going one direction and a half arrow going another direction. Now, let's take a look at this overall. If you take a look at any expression, we're going to use this expression AA, BB, CC, DD. We can write what we call the equilibrium expression, which is also known as the law of mass action, which is kind of confusing. But we can draw this by going like this. We can say K is equal to, and what we always do is, if you take a look at here, do the alphabet, LMNO PQR, and that means that we put our products on top of our reactants. So our products in this case are RC and RD. And so we're going to multiply them like this, but the coefficients we write as their exponents. Same thing over here. On the bottom, we're going to write A raised to the A, B raised to the B. The K equilibrium, this right here, this is the equilibrium constant. I'm having trouble writing, so I'm going to stop writing here. And the square brackets represent molar concentration. Now, I want you to pause for a second, and I want you to write the equilibrium expression for this right here. If you've tried it, then in this case here would be K. And we write little equilibrium, we write the subscripts here to let us know what's going on. We write K is equal to, and we write NH3 because it's on the product side. We write that raised to the power 2 because that's its coefficient right here. And on the reactant side, remember it's always PQR, it'd be N2 raised to the 1, which is just 1. And we don't have to write anything. And we have H2 raised to the 3. Now, again, it's really, really important you have a balanced equation. Now, what's not included ever, you never include liquids, and you never include solids. Now, you're wondering, like, what the heck? How does that work? Well, the reason we do that is because solids and liquids, we consider them to have a value of 1, and the K takes care of them. Now, this little expression here, solvents of dilute solutions, we're not going to worry about that right now. Other thing I want you to be aware of here is this. Do you realize that every single time your K is always going to have your products on the top? So if I do K, what you're going to have is products on the top, and you're going to have reactants on the bottom. Right? And I'm going to put concentration here. And this is not entirely accurate because you'd be raising it to their powers, right? So you're going to have these two things here. Now, what that means is that if my K is bigger, wouldn't that mean I have more products and less reactants, just if you're doing it mathematically? And if my K is smaller, I'm going to have more reactants and less products. So the equilibrium constant for an equilibrium shows how complete. If the constant is large, we assume that we have completely converted to products at equilibrium. Now, another way of saying this is when the K is greater than 1, products are favored. And when the K is less than 1, reactants are favored. The other thing you need to be aware of is this. Fast reaction go has nothing to do with K. All K does is it gives us a relationship, and I'm going to do a highlight here. It gives a relationship between our products and our reactants. That's the worst highlighting color ever. Anyway, we're going to come back to this, and the idea is simply this. The K determines how much product versus reaction we always have. Hopefully this has helped. We'll jump back in a minute.